Let's set the band in motion. Last time we built a band from a chain of atoms. We started with an electron that could sit at any site, let it hop to its neighbours, and out came a curve. The energy E of K equals E0 minus 2t cosine of Ka. We labelled every possible state by a twist K, living inside one Brillouin zone. But here's the thing that should have been nagging us the whole time. We built a map of all the states, and we never once made the electron actually go anywhere. Today, we let it loose. George, by the end of this, we're going to make an electron that speeds up, then mysteriously slows down, and then, this is the one I can't get over, pushes back the wrong way when you shove it.
We are. And every single one of those surprises is going to come from just two things: the slope of that band curve and its curvature. That's the whole toolkit today. In part 1, we drew the curve. In part 2, we read its shape. The slope of E of K is going to be velocity, how fast the electron moves. The curvature, how the slope is changing, is going to be mass, how hard it is to push. And then we count electrons against states, and we get the biggest payoff of all: why some solids conduct electricity and some don't. Same curve, 3 questions.
Let me start with a problem that I think trips people up because it tripped me. In part 1, a state of definite K, a definite twist, was spread evenly over the entire chain. Every site had an arrow of the same length. So in what sense does that electron move? It's already everywhere.
That is exactly the right worry, and confronting it is the doorway to today. You're completely right. A pure K state, a single definite twist, is spread over the whole lattice with equal probability at every site. It's a standing pattern. It has an energy, it has a crystal momentum, but as a lump of, here is the electron, it doesn't go anywhere. There's no bump to follow. So if you want a localized electron, something that's here and then over there a moment later, one pure twist won't do it. You have to build a package.
A package out of what? Out of many twists?
Out of many nearby twists. This is the idea of a wave packet, and it's worth building slowly. Take not one value of K, but a narrow spread of them, all clustered around some central twist. Call it K0. Add those waves together. Where their crests line up, they reinforce and you get a bump. Everywhere else, they fall out of step and cancel. So a bundle of nearby twists interferes into a single localized lump sitting somewhere on the chain. That lump, that's your electron as a particle. And now the question, how fast does the electron move, becomes a real answerable question. How fast does that lump slide along the lattice?
And I'm guessing the lump does not move at the same speed as the underlying ripples inside it.
It does not, and that distinction is one of the deepest little facts in all of wave physics. Inside the packet, the individual crests march along at one speed, the phase velocity. But the envelope, the outline of the bump, the thing that actually carries the electron and the energy, moves at a different speed, the group velocity. Picture ocean swell. The little wrinkles race through the group, but the group itself, the set of big waves, travels slower. For us, the electron is the group. So the speed we care about is the group velocity.
And there's a clean formula for the group velocity in terms of our band.
There's a beautiful one, and it's the first headline of the episode. The group velocity is 1 over h bar times the derivative of the energy with respect to K. In words, the velocity of the electron is the slope of the band curve divided by h bar. Write it as V of K equals 1 over h bar times dE by dK. The slope of E of K is the speed. That's it. If you know the shape of the band, you know how fast an electron in each state moves. You just read off the steepness.
Let me make sure I believe the slope is speed idea before we compute it. Why the slope? Where does that come from?
Here's the intuition without heavy machinery. A quantum wave's frequency is its energy divided by h bar. That's the de Broglie-Planck relation. Energy is h bar times frequency. And there's a general theorem about wave packets from any kind of wave. The envelope of a packet moves at the rate that the frequency changes as you change the wave number, the derivative of frequency with respect to k. Put those together. Frequency is energy over h bar, so the rate frequency changes with k is 1 over h bar times the rate energy changes with k. And that's the group velocity, 1 over h bar dE by dk. So, slope of the band is speed, is really how fast the wave's frequency ramps up as you wind the twist tighter, which is exactly what sets how fast a packet slides.
You slipped in. A quantum wave's frequency is its energy over h bar. I don't want to take that on faith. Where does it come from?
It comes from the founding relation of quantum mechanics from Planck and Einstein. The energy of a quantum wave is h bar times its frequency. Energy equals h bar omega, where omega is the angular frequency. A particle of light, a photon, has energy equal to Planck's constant times its frequency. An electron wave obeys the very same rule. So frequency and energy are the same quantity, wearing different clothes, tied together by that factor of h bar. That's exactly why the energy band, E of k, doubles as a frequency map. And it lets me sharpen the phase versus group distinction with real formulas. The phase velocity, how fast a single crest travels, is the frequency divided by the wave number, the energy over h bar k. The group velocity, how fast the envelope travels, is the derivative, 1 over h bar dE dk. Those are different numbers. For an ordinary free particle whose energy is momentum squared over 2m, if you work them out, the group velocity comes out to exactly twice the phase velocity. The bump outruns its own ripples. So it's a real physical distinction, not just bookkeeping.
Good, I'll take it. Now let's actually do it for our band. We have E of k equals E0 minus 2t cosine of Ka. Take the slope.
Let's turn the crank, it's quick. We need the derivative of E0 minus 2t cosine of Ka with respect to k. The E0 is a constant, so it contributes nothing to the slope. The derivative of cosine of Ka with respect to k is minus a sine of Ka. The a comes down from the chain rule. So the derivative of minus 2t cosine of Ka is minus 2t times minus a sine of Ka, which is plus 2t a sine of Ka. So the slope, dE by dk, is 2t a sine of Ka.
And then the group velocity is that slope over h bar.
Exactly. The group velocity, v of k, is 2t a over h bar times sine of Ka. And now, this is where it gets fun, let's just read the shape of that. It's a sine. So let's walk k across the Brillouin zone and watch the speed.
Start me at the bottom of the band. K equals 0.
At k equals 0, remember that's the bottom of the band, the smooth, all arrows aligned state. Sine of 0 is 0, so the velocity is 0. The electron at the very bottom of the band sits still. Which makes sense. It's the ground state of the band, the calmest, most spread out configuration. No motion.
Now push K up a bit, toward the middle of the zone.
As k increases from 0, sine of Ka grows, so the velocity grows. The electron moves faster and faster. For small k, it's essentially proportional to k, which is exactly the free particle behavior we found lurking at the bottom of the band in part 1, where the band looked like a parabola and the electron acted ordinary. So far, so normal. More twist, more speed. The velocity keeps climbing until Ka reaches pi over 2, the middle of the zone, where sine hits its maximum of 1. That's the fastest the electron ever goes, 2Ta over h bar.
Put a real number on that top speed. Is it actually fast or fast for an electron?
Let's estimate it. For a typical solid, the hopping t is something like an electron volt, and the lattice spacing A is a few angstroms, a few tenths of a nanometer. Feed those into 2 Ta over h bar, and you get a speed on the order of a few hundred kilometers per second. That is genuinely, physically fast. It's comparable to the actual speeds of the most energetic electrons in a real metal, the ones sitting right at the top of the filled states. So this isn't a cartoon quantity. The middle of a tight binding band really does move its electrons at hundreds of kilometers a second, and that speed is set by nothing more than how strongly neighboring atoms are coupled and how far apart they sit. Turn up the hopping, widen the band, and your electrons literally go faster.
So the top speed is right in the middle of the band. And now the part that I know is coming but still feels wrong. Keep going toward the top.
Keep pushing K past the middle, past Ka equals pi over 2, on toward the zone edge at Ka equals pi, and sine of Ka starts coming back down. The velocity decreases, and right at the zone edge, Ka equals pi, the top of the band, the staggered plus minus state from part 1, sine of pi is 0 again, so the velocity is back to 0. The electron at the very top of the band, just like the one at the very bottom, doesn't move at all.
That is genuinely strange. I put more and more twist into the electron, more crystal momentum, and past the middle of the band it responds by going slower, and at the top it's frozen. A free electron in empty space just goes faster and faster forever. The lattice caps the speed and then throttles it back down.
The lattice throttles it back down, and that is the first deep lesson of the dynamics. Velocity is the slope of the band, and a band, unlike a free particle parabola, bends over and flattens out at the top. Where the band is steep, the middle, the electron is fast. Where the band is flat, both edges, the electron is stationary. The speed isn't tied to how much momentum you've piled in. It's tied to the local steepness of the energy curve. That's a purely lattice phenomenon, and we'll see in a moment it has a spectacular consequence.
Before we get there, I want to connect it to the phasor picture from part 1, because that's been our through line. Is there an arrow picture for why the top of the band is frozen?
There is, and I like it. Remember, the group velocity comes from nearby twists interfering to make a packet, and the packet slides because the twist pattern shifts from site to site as time goes on. At the very bottom of the band, all the arrows are aligned and barely winding. There's no net direction for the pattern to march. At the top, the arrows are flipping a full half turn every single site. The pattern is as wound up as the lattice can represent. It's a standing wave of maximal staggering, and a maximal standing wave has no net travel either. The left-going and right-going pieces are perfectly balanced. It's in the middle, where the winding is moderate and lopsided, that the pattern genuinely streams along. Fast in the middle, frozen at both ends.
Why is the zone edge special enough to make a perfect standing wave? Is that about the lattice, or just the math of a sine hitting 0?
It's about the lattice, deeply. It's diffraction, the very same physics as light bouncing off a grating. At the zone edge, the electron's wavelength is exactly 2 lattice spacings. 1 atom up, 1 atom down, and the pattern repeats. And that is precisely the condition for the wave to reflect off the regular array of atoms, what's called Bragg reflection. A wave traveling to the right at that special wavelength gets bounced into a wave traveling left, just as strongly, again and again off every atom. The right-goer and the left-goer combine into a standing wave that goes nowhere, which is exactly why the group velocity is 0 at the edge. So the frozen top of the band isn't a coincidence of the sine function. It's the electron being perfectly mirror-reflected by the lattice itself. And that same Bragg reflection at the zone boundary is, in the fuller theory, the thing that pries open the energy gaps between bands. The edge of the zone is where the lattice grabs the electron hardest.
Beautiful. Okay, so we have velocity from the slope. Now you promised me the electron pushes back the wrong way. To get there, we have to actually push it. How do you push an electron in this framework?
You apply a force, the most natural one being an electric field, which pushes on the electron's charge. And here's the rule for what a steady force does, and it's deceptively simple. The force changes the crystal momentum at a constant rate. h bar times dk by dt equals the force F. In words, push on the electron and its k, its twist label, increases steadily in time. The electron walks through the Brillouin zone at a constant pace, set by the force.
Wait, the force changes k, the twist, rather than directly changing the velocity. That's already not what I'd expect from ordinary mechanics, where force changes velocity.
That's the subtlety, and it's the whole story. In ordinary mechanics, force equals mass times acceleration, so force feeds straight into velocity. Here, the force feeds into k, the crystal momentum, at a constant rate. And then the velocity is whatever the band says it is at that k, through our slope formula. So the force marches the electron along the horizontal axis of the band, through the zone, and the electron's actual speed just follows the terrain of the curve as it goes. Force moves you along k. The band's slope at each k tells you how fast you're going there. Those are two separate steps now, and pulling them apart is the key to everything strange that follows.
So let me find the acceleration, the actual change in velocity, by chaining those two steps together.
Let's do it. It's a lovely little chain rule. The acceleration is the rate of change of velocity in time. Velocity depends on k, and k depends on time, so the acceleration is the derivative of velocity with respect to k, times the rate k changes in time. The derivative of velocity with respect to k? Well, velocity is 1 over h bar times the slope of e, so its derivative is 1 over h bar times the second derivative of e, the curvature. And the rate k changes in time, we just said, is the force over h bar. Multiply them. The acceleration is 1 over h bar squared, times the curvature of the band, times the force.
So acceleration equals the curvature of E of k over h bar squared times the force. Compare that to Newton, force over mass, and you can just read off an effective mass.
You read it right off, and this is the second headline. Newton says acceleration is force divided by mass. We just found acceleration is force times the curvature of the band over h bar squared. So the thing playing the role of 1 over the mass is the curvature of the band divided by h bar squared. We write it. 1 over m star equals 1 over h bar squared times the second derivative of e with respect to k. That m star is the effective mass, the mass the electron appears to have when you push it, and it is set entirely by how sharply the band curves.
Curvature is mass. Let me feel that before we compute. Sharp curve versus gentle curve. Which is heavy?
Think about it through the formula. 1 over the mass is the curvature. So a sharply curved band, big curvature, means a big 1 over mass, which means a small mass. A light electron. A gently curved, nearly flat band means small curvature, tiny 1 over mass, huge mass. A heavy, sluggish electron. This matches the seed we planted in part 1 exactly. Strong hopping made a steep, sharply curved parabola at the bottom and a light electron. Weak hopping made a shallow band and a heavy one. Curvature and mass are inverse. A tightly curved band is a nimble electron. A flat band is a lead weight.
Is this effective mass a real, measurable thing, or a bookkeeping trick? If I could weigh an electron in a crystal, would it actually come out different from an electron in vacuum?
It is utterly real and routinely measured. It's one of the most important numbers you can quote about a material. When an electron moves through a crystal, every experiment that probes how it responds to a force, how it bends in a magnetic field, how it absorbs light, how its heat capacity behaves, sees the effective mass, not the vacuum mass. And the numbers are startling. In gallium arsenide, the workhorse of fast electronics, the conduction electrons behave as though they weigh only about a 15th of a free electron. They're feather light, which is exactly why that material makes such fast transistors. Light electrons accelerate easily. Go the other way, and there are materials called heavy fermion compounds, where the bands are so flat that the electrons stagger around as if they weigh hundreds of times the vacuum mass. Same particle, same true mass, but dressed in the lattice, it can be a sprinter or a slug, depending entirely on how its band curves. The effective mass is where our whole curvature story stops being a diagram and starts being a dial that materials scientists actually turn.
All right, now compute the curvature for our band, and let's see the effective mass across the zone.
We need the second derivative of E of k, the derivative of the slope. The slope we found was 2t a sine of ka. Take its derivative with respect to k. The derivative of sine of ka is a cosine of ka, and the a comes down again, so we get 2ta squared cosine of ka. That's the curvature. So the effective mass, m star, is h bar squared divided by that curvature. H bar squared over 2ta squared cosine of ka. And now, once again, the whole story is in that cosine. Let's walk the zone.
Bottom of the band first, k equals 0.
At k equals 0, cosine of 0 is 1, so the effective mass is h bar squared over 2ta squared, a positive number and a smallish one if the hopping t is big. Positive mass, light electron, behaves like an ordinary particle. That's the free particle bottom of the band we keep coming back to. Push it forward, it accelerates forward. Totally normal. Now let's climb.
Move up to the middle of the zone. Ka equals pi over 2.
At Ka equals pi over 2, cosine is 0, and the effective mass is h bar squared over 0. The mass blows up to infinity. At the inflection point of the band, right where the curve is straightest, the electron behaves as if it has infinite mass. You push on it, and it does not accelerate at all, momentarily. It's the point where the band has switched from curving upward to curving downward, and right at the switch there's no curvature, so no response. An immovable electron.
Infinite mass in the middle. And I know where this is going, but say it, the top of the band.
Push k past the middle, toward the zone edge, and the cosine of Ka goes negative, which means the effective mass goes negative. Near the top of the band, m star is a negative number. Concretely, right at the edge, it's minus h bar squared over 2ta squared. The electron has negative effective mass. You push it forward with a force, and it accelerates backward.
Okay, I need to sit with that, because it sounds like it breaks physics. I push the thing east and it goes west. Where did the momentum go? What is actually happening?
Nothing breaks, and the resolution is exactly the two-step separation we set up. Remember, the force still increases k steadily. That part is completely normal. The crystal momentum keeps marching east. But near the top of the band, the velocity, which is the slope, is decreasing as k increases. We saw that, sine coming back down past the middle. So, as the force dutifully pushes k higher, the electron's actual speed drops, and then reverses. The electron slows, stops, and turns around, even though you never stopped pushing. In terms of apparent mass, that responds opposite to the push is exactly what a negative mass means.
But physically, where's the eastward momentum you keep feeding in going if the electron heads west?
Into the lattice. This is the whole point of crystal momentum being different from true momentum, which we flagged back in part 1. The electron and the lattice exchange momentum in the lattice's own units. Near the top of the band, the electron is so strongly diffracted by the periodic array of atoms, it's near that maximal staggering, standing wave condition, that the lattice hands momentum back to it in the opposite direction, faster than your field feeds it in. The lattice is a participant, not a passive stage. So the electron's response to your push is dominated by its conversation with the atoms, and near the band top, that conversation runs backward. Push east, the lattice pushes west harder, net motion west. Negative effective mass is just the tidy bookkeeping for the lattice is winning the momentum argument.
That is one of the most beautiful things I've heard. And I have a hunch this negative mass business is not a curiosity. It has a name downstream.
It's the seed of one of the most useful ideas in all of solid-state physics. Holes. When you have a band that's nearly full and the empty states are up near the top, where the mass is negative, it turns out to be far cleaner to stop tracking the many negative mass electrons and instead track the few empty spots as if they were positive particles. Those empty spots, holes, act like positive charges with positive mass. Every transistor, every semiconductor diode is built on electrons and holes exist because the top of a band curves the other way and hands you negative effective mass. We won't build the whole theory today, but I want you to see that the strangeness we just derived is load-bearing. It's the foundation of the entire electronics industry.
Give me a picture for a hole, because track the empty spot as a positive particle sounds like a mathematical dodge. Why is the absence of a negative mass electron a genuine positive particle?
Think of a nearly full row of seats in a theatre with one empty chair. If everyone shuffles one seat over to fill the gap, the people all moved left. But what you actually notice, the thing your eye tracks, is the empty seat moving right. The absence travels the opposite way to the crowd, and it travels as a clean single object even though 100 people did the shuffling. A hole in a band is exactly that empty seat. A swarm of electrons shifts one way, and the missing state glides the other way, behaving like one tidy particle. And because the electrons that are doing the shuffling near the top of the band have negative charge and that awkward negative mass, when you do the arithmetic, the empty spot comes out with the opposite of both. It carries positive charge and positive mass. So it's not a dodge at all. It's the simpler, truer description. In fact, you can catch holes red-handed. Run a current through a semiconductor in a magnetic field and measure the sideways voltage, the Hall effect, and the sign of that voltage tells you whether the current is really being carried by negative electrons or by positive holes. In many materials, it comes out positive. The lattice really is conducting by moving absences around, and you can read the sign right off a meter.
Let me flag one more consequence, because you set up a steady force marching K across the zone, and I keep thinking about what happens when K reaches the edge. In part 1, we learned K is periodic, the zone wraps around. So what happens to an electron you just keep pushing?
Oh, this is my favorite prediction in the whole subject, and you've spotted it exactly. Apply a constant force, a steady electric field, and K increases linearly forever. But K lives in the Brillouin zone, and the zone wraps. When K reaches the edge at pi over A, it's identical to the state at minus pi over A, the other edge, and it just re-enters from the other side. So K sweeps across the zone, wraps around, sweeps across again, round and round at a constant rate. And the velocity, which is that sign of Ka, therefore oscillates. Positive, back to zero, negative, back to zero, positive again. The electron's speed cycles.
So a constant force, a steady direct current push, produces an oscillating velocity. The electron doesn't run away, it rattles back and forth.
It rattles back and forth in real space. A steady direct current force produces alternating current motion. The electron accelerates, slows, reverses, comes back, over and over. It oscillates in position instead of flying off. These are called Bloch oscillations, and they are the single most counterintuitive prediction of band dynamics. Shove a crystal's electron with a constant field, and left alone, it just wobbles in place. The period of the wobble gets shorter the harder you push.
Can we pin the period down? You said harder push means faster wobble. What exactly sets the timing?
We can get it from the rule we already have, and it's clean. The force marches k across the zone at the rate force over h bar, and one full oscillation is one complete trip across the zone, a span of 2 pi over a in k. So the period is just the width of the zone divided by the speed you cross it. That works out to Planck's constant divided by the force times the lattice spacing. Written out, the Bloch period is h over the force times a. Read it off. Bigger force, shorter period. Push harder and the electron wraps the zone faster, so it wobbles faster, exactly as intuition wanted. And there's a companion number, the amplitude, how far the electron actually swings in real space. That comes out to be the width of the band divided by the force. So a wider band, a bigger 4T, lets the electron range farther before it turns around, and a stronger force clamps it into a tighter wiggle. Two tidy formulas. The period is Planck's constant over force times spacing. The swing is bandwidth over force. Everything about the wobble is set by the band you built and the force you apply.
Then why doesn't my copper wire wobble instead of carrying current? Because it plainly carries current.
Because in a real metal, the electron never survives a full trip across the zone. It's constantly getting scattered, bumping off vibrations of the lattice, off impurities, off defects. And each collision resets its K long before it can wrap around. So in ordinary materials, the beautiful Bloch oscillation is cut off almost immediately, and what you get instead is a slow net drift. That's your electric current. The oscillation is real, but it's usually killed in the cradle by scattering.
Usually, which means somebody found a place clean enough to actually see it.
Somebody did, and this is where it touches our own world. If you build an artificial lattice clean enough and drive it fast enough, the electron completes its zone crossing before it scatters, and the Bloch oscillation becomes visible. It's been seen in engineered semiconductor superlattices and, this is the one close to home, in ultra-cold atoms sitting in an optical lattice, a crystal made not of atoms but of interfering laser beams, the very system a lot of our work lives in. There, with no defects and exquisite control, you can watch atoms Bloch oscillate cleanly, exactly as this theory predicts. The wobble that copper hides, a laser lattice shows you in the open.
How do you actually watch it? An atom wobbling by a few lattice sites is impossibly small to see with your eyes. What's the trick?
The trick is beautiful, and it plays right off everything we built today. You take a cloud of ultra-cold atoms and load them into the optical lattice, the standing wave of laser light. Then, to supply the constant force, you don't use an electric field, because the atoms are neutral. Instead, you simply tilt the lattice, often by just letting gravity pull along it, or by gently sliding the laser pattern so the atoms feel a steady pull. That plays the role of our force F, marching every atom's K across the zone together. Now here's the clever readout. Rather than trying to watch the tiny real space jiggle, you measure the atom's velocity, their momentum, which is what oscillates. You switch off all the lasers, let the cloud fly freely for a moment, and take a picture. How far each atom has drifted in that free flight tells you exactly how fast it was going at the instant of release. That's called time-of-flight imaging. Do it again and again at different moments in the cycle, and you watch the whole momentum distribution slosh back and forth, positive to negative and back, ticking at precisely the Bloch period we just wrote down. So the abstract sine wave velocity from our band curve becomes a cloud of atoms visibly surging one way, then the other, in a camera image. The whiteboard curve photographed.
I love that the messiest everyday material buries the effect, and the pristine designer lattice reveals it. Okay, we've got motion from the slope, mass from the curvature, and this gorgeous oscillation. There's one more promise from part 1 I want to collect. You said our plane wave guess, the twist Cn equals e to the ikNa, was secretly a special case of a big theorem. Time to name it.
Time to name it. Bloch's theorem. And it's one of the load-bearing pillars of the physics of solids. Here's the statement. Take any electron in any perfectly periodic potential, a real crystal, atoms repeating forever. Bloch's theorem says every energy eigenstate can be written as a plane wave, e to the I kx, multiplied by a function u sub k of x that has the same period as the lattice. In symbols, psi sub k of x equals e to the I kx times u sub k of x, where u repeats every lattice spacing. A travelling wave wearing a periodic costume.
Unpack. A travelling wave wearing a periodic costume. What are the two pieces doing?
Two jobs, cleanly separated. The e to the I kx piece is the smooth, long-range travelling wave. It's what carries the electron across the crystal, and its k is exactly our twist, our crystal momentum. The u sub k of x piece is the local detail, how the electron's wave function wrinkles up around each atom, the shape it takes inside a single unit cell. It repeats identically from cell to cell because every cell is the same. So a Bloch state is march across the crystal with a steady phase twist, and within each cell do the same local dance. The global travel and the local atomic detail multiplied together.
And our tight-binding twist was which piece?
Ours was the e to the I kx piece, sampled at the atomic sites. When we wrote Cn equals e to the I kNa, that e to the I kNa is precisely the travelling wave phase evaluated at site n, position n times a. And the u part, the local shape, was hidden inside our assumption that the electron sits in one atomic orbital at each site. We never wrote it out because we treated each site as a single blob. So tight binding is Bloch's theorem, with the costume simplified to one orbital per atom. The full theorem just says, you're always allowed to peel any crystal eigenstate into a twist times a periodic local shape. Our whole part 1 was one clean instance of it.
What does that local costume, the u sub k of x, actually look like? Can you help me picture it sitting on top of the travelling wave?
Picture two length scales living together. The e to the I kx part is a long, smooth swell. Its wavelength can stretch across many, many atoms, and it's what winds the phase slowly as you walk down the crystal. Then riding on top of that swell is u sub k of x, a short, repeating wrinkle that looks the same in every unit cell. It dips down toward each atomic nucleus, where the electron likes to be, and rises between atoms. So the full wave function is a gently gliding wave whose fine texture snaps back to an identical little shape at every atom. If you slid one lattice spacing over, the smooth swell would have advanced its phase a touch, but the local wrinkle would look exactly as it did at the previous atom. And here's a lovely consequence. The number of little nodes, the wiggles that the local part packs inside each cell, is what distinguishes one band from the next. The lowest band has the smoothest local shape, no extra nodes. The next band up has one more node crammed into every cell. The one above that has two, and so on. Higher bands are more wrinkled at the atomic scale. So bands aren't just stacked energies, they're a ladder of increasingly nodey local costumes, all riding the same kind of travelling swell.
That reframes everything we did as a special case of something universal. Now, the word is bands, plural, and so far we've built exactly one band from one orbital. Where do the others come from?
From the other orbitals. We let each atom contribute a single state, call it the s orbital, and hopping between those s orbitals smeared that one atomic level into one band, of width 4t. But a real atom has more available levels: p orbitals, d orbitals, higher s orbitals. Each of those, repeated across the lattice and broadened by its own hopping, becomes its own band. So you get a stack of bands, one per atomic orbital, each broadened into a range of allowed energies and, crucially, separated by gaps, ranges of energy where there are simply no allowed states at all.
Where do the gaps come from physically?
From the spacing of the original atomic levels versus how much the hopping smears them. Each atomic level broadens into a band whose width is set by the hopping, how easily electrons move between neighboring atoms in that orbital. If the atomic levels start far apart and the hopping is modest, each one broadens a little and there's left over empty energy between them, a gap. If the hopping is huge, adjacent bands can widen until they touch or overlap and the gap closes. So the band structure of a real solid is just this, a set of allowed energy bands, one family per orbital, with forbidden gaps in between, and the widths and gaps are set by the atoms and how strongly they're coupled. That picture, bands and gaps, is the skeleton of the electronic structure of every crystalline solid.
Make the multi-orbital thing concrete for me. If a single s orbital gave us one band, what does a p orbital give? And does it look different?
It looks richer, and the difference is geometric. An s orbital is a simple round blob, spherically symmetric, so it hops to its neighbors the same way in every direction, and it broadens into a single band, exactly the one we built. But a p orbital is not round. It's dumbbell-shaped, with a lobe pointing one way and an opposite lobe pointing the other. And crucially, in 3 dimensions, there are 3 of them, pointing along the 3 perpendicular directions. Call them the x, y, and z dumbbells. Each one hops differently depending on whether it's pointing along the chain or across it. A dumbbell aimed down the chain overlaps its neighbor strongly, tip to tip, while one aimed sideways barely reaches. So those 3 p orbitals broaden into a set of 3 p bands with different widths, all sitting above the s band. That's why real band structures aren't one lonely curve. They're a dense thicket, an s band down low, a bundle of p bands above it, d bands above those, sometimes overlapping, sometimes gapped. Every one of them is our same tight binding story. A level, its neighbors, a hop, just run in parallel for each shape of orbital the atom offers. The single band we built is one thread pulled out of that whole tapestry.
And now we're finally in position for the grand payoff you promised at the very start of part 1, why some solids conduct and some don't. We have bands, we have states. The missing ingredient is the electrons themselves. How do we fill this up?
We fill it with the one rule that governs electrons. They're fermions, so no two can occupy the same quantum state. The Pauli exclusion principle. Now let's count states carefully, because the whole answer is a counting argument. In part 1, we found that a chain of n atoms gives exactly n distinct values of k in the band, n states. But each of those k states can actually hold 2 electrons, not 1, because the electron also has spin. It can be spin up or spin down, and those are 2 different states. So each band has room for 2 n electrons, n sites, 2 n electron slots per band.
And you fill from the bottom up because low energy is preferred.
From the bottom up, you pour the electrons in and they settle into the lowest available states first, stacking up until you run out of electrons. The energy of the highest filled state, the waterline, has a name, the Fermi level. And here is the entire secret of whether something conducts. It comes down to where that waterline sits. Does it land in the middle of a band, or exactly at the top of a full band with a gap above it?
Let's take the 2 cases. Suppose each atom donates 1 electron to this band. Then I have n electrons and 2 n slots. The band is half full.
Half full, and that is a metal. The waterline, the Fermi level, sits right in the middle of the band, and here's why that conducts. Just above the highest filled state, there are tons of empty states at essentially the same energy. So when you apply an electric field, a gentle push, electrons at the waterline can slip into those nearby empty states, shift their k a little, and pick up a net velocity. The population becomes lopsided, more electrons moving one way than the other, and that imbalance is an electric current. Empty states right next door means the electrons can respond to a push. A partially filled band conducts. That's a metal. Think copper, sodium, one loosely held electron per atom.
Hold on. You said the waterline sits in the middle of the band, but it's a whole surface of states at that energy, isn't it? Where exactly does the filled part stop?
Good. Let's be precise about the waterline, because it matters. In our one-dimensional band, the states are strung out along the k-axis, and their energy is that cosine curve. When you fill from the bottom with the half band's worth of electrons, you fill the lowest energy states, and those live near the center of the zone, around k equals 0, where the band is lowest. You keep filling outward in k until the electrons run out. For a half-filled band, the filling reaches exactly out to k equal to plus and minus pi over 2a, halfway to the zone edge on each side. Those two special points, where the filled states stop and the empty ones begin, are the Fermi points. In one dimension, it's just 2 points. In a real three-dimensional metal, that boundary between filled and empty isn't 2 points, but a whole surface in k-space, the famous Fermi surface, and essentially all of a metal's electrical life happens right at that surface, because that's where the empty states sit next door to the filled ones. So, the waterline in the middle of the band sharpens to the Fermi points at plus and minus pi over 2a, and it's the electrons right there, at the edge of the filled region, that carry the current when you push.
Now, the other case, each atom donates 2 electrons. N atoms, 2 n electrons, 2 n slots. The band is exactly full.
Exactly full, right to the brim, with a gap above it, and that is an insulator. And the reason it can't conduct is gorgeous. Apply your electric field, try to push the electrons, but every single state in the band is already occupied. There is no nearby empty state to slip into. To respond to the field, an electron would have to jump all the way across the energy gap to the next empty band, and a gentle field can't supply that. So nothing shifts. And there's an even cleaner way to see it. A completely full band carries exactly 0 current, always, because for every electron moving right with velocity from some plus k, there's another electron in the minus k state moving left at exactly the opposite velocity. Remember, the velocity is that odd sine function. Sine of minus ka is minus sine of ka. Every mover is perfectly cancelled by its mirror twin. A full band is a perfectly balanced, current-free thing. No push can unbalance it without crossing the gap.
Let me push back because I don't fully feel the difference yet. In both cases, I apply a field to a band full of electrons. Why can the half-full band shift its balance, but the full one can't?
That's the right question to press on, and the answer is all about having somewhere to go. Picture the electrons laid out along the k-axis, and think of the field as trying to slide every electron's k in the same direction. Shove the whole occupied population a little toward positive k. In the half-full band, the occupied region is a block in the middle, from minus pi over 2a to plus pi over 2a, with empty states on both ends. The field slides that block slightly. Some electrons fall off the trailing edge into empty states, others advance at the leading edge into empty states. Now there are a few more electrons moving right than left. The mirror symmetry between plus k and minus k is broken, and that imbalance is a current. It works precisely because there were empty states at the edges for the block to slide into. Now the full band. The occupied region is the entire zone, edge to edge. Try to slide it toward positive k, and an electron pushed off the top edge at plus pi over a has nowhere new to go. Because of the zone wrapping, it just reappears at minus pi over a, which was already occupied. The band is a closed loop that's completely full. Sliding it maps it onto itself and changes absolutely nothing. Every plus k still has its minus k partner. The velocities still cancel in perfect pairs, and the current stays stone-dead zero. The half-full band conducts because its filled region has an edge to shift. The full band can't shift at all because it has no edge and nowhere to shift into.
So it's not about having electrons or not. The insulator is packed with electrons. It's about whether there's anywhere for them to go.
That is exactly it, and it's the crux of the whole subject. Conduction isn't about how many electrons you have. An insulator like diamond is stuffed with them. It's about whether there are accessible empty states right next to the filled ones. A partially filled band has them, metal. A full band with a gap above does not, insulator. And a semiconductor, silicon, is just an insulator with a small enough gap that a little heat or a little doping can kick a few electrons across it and give you a trickle of conduction you can control. The entire distinction between a copper wire and a diamond and a silicon chip is the answer to one question. Given the bands and the electron count, is the topmost occupied band partly empty or exactly full?
I want to test the rule because it sounds almost too tidy. It says an even number of electrons per atom fills bands exactly and gives an insulator. But magnesium and calcium each donate 2 electrons per atom, even numbers, and they're both good metals. Doesn't that break your rule?
It's a fair challenge, and it sharpens the rule rather than breaking it. The counting argument tells you an even number of electrons is exactly enough to fill a whole number of bands, but only if the bands stay cleanly separated by gaps. In magnesium and calcium they don't. Remember we said that when the hopping is strong, neighboring bands can widen until they overlap in energy. That's what happens there. The band that should have been filled and the next band up overlap, so instead of one full band with a gap above, you get 2 partly filled bands sharing the electrons. Partly filled means empty states next door, means conduction, so they're metals despite the even count. So the precise rule isn't even means insulator. It's this. You get an insulator only when the electrons exactly fill a set of bands and there's a real gap above the highest filled one, with no overlapping band poking down into it. Even filling is necessary, but you also need the bands to stay out of each other's way. When they overlap, all bets are off and you get a metal.
And the in-between case, the semiconductor, is that just about how big the gap is?
Precisely. It's a full band with a gap, but a modest one. Silicon has its lower bands exactly filled, with a gap above of a bit more than an electron volt. At absolute zero, that makes it a perfect insulator, nothing in the empty band. But that gap is small enough that ordinary warmth, room temperature thermal energy, kicks a handful of electrons up across it into the empty band above. Now you've got a few electrons rattling around up top and a few holes left behind down below. A trickle of conduction and one you can dial. Compare that to diamond, chemically silicon's cousin, whose gap is several electron volts, far too wide for heat to bridge, so diamond stays a stubborn insulator and stays transparent. And the real magic of silicon is that you don't have to rely on heat. You can dope it, sprinkle in a few atoms with 1 extra electron to spare, that's N-type, or a few with 1 too few, leaving eager holes, that's P-type, and tune exactly how many carriers you get and of which sign. Set an N-type region against a P-type region and you've built a diode. Layer them and you've built a transistor. So that one small gap, sitting between the metals with no gap and the insulators with a big one, is the entire foundation of the semiconductor age. And it's nothing more than the band-filling question we just answered, asked about a band with a conveniently narrow gap above it.
Let me try to say the whole 2-part journey back, because it actually closes a loop now. In part 1, we took a chain of atoms, let an electron hop, and got a band, the curve E of K, with all its states labelled by a twist K in the Brillouin zone. Today, we read that curve's shape. Its slope is the electron's velocity, which is fast in the middle of the band and frozen at both edges. Its curvature is the electron's effective mass, which is light and positive at the bottom, infinite in the middle, and negative at the top, where the lattice pushes back harder than you push and hands you the idea of holes. A steady force marches the electron across the zone and, in a clean enough lattice, makes it oscillate in place. And when we finally poured real electrons in, 2 per state, filling from the bottom, the single question of whether the top band is partly empty or exactly full became the difference between a metal and an insulator.
That's the whole arc, and it all came off the shape of one curve. That's the thing I'd want anyone to walk away with. We drew a single band in part 1 from almost nothing. A sight, a neighbour, a hop. And in part 2, the slope of that band gave us motion, the curvature gave us mass, the periodicity gave us Bloch oscillations, and the filling gave us the metal-insulator divide. Bloch's theorem told us this wasn't a toy. The same twist times periodic shape structure is how every crystalline solid works. From a chain of wells to why your wire conducts and your window doesn't, all of it is reading the slope, the curvature, and the waterline of E of K.
And the tie back to the lab is that the cleanest place to watch these predictions naked, the Bloch oscillations especially, is an artificial crystal of light holding cold atoms, which is the kind of machine a lot of this program runs on. The chain we drew on a whiteboard, you can now build with lasers and watch it dance.
You can build it and watch it obey every line of what we just derived. The band, the group velocity, the oscillation. Which is a good place to leave it. The tight binding chain isn't just a teaching toy, it's a real buildable quantum system, and its whole dynamical life is written in the slope and curvature of one curve.
Then that's the series, build the band, then set it in motion. Thanks for sticking through both halves, everyone. Next time you hold a copper wire and a piece of glass, picture the same band in each, filled 2 different ways. That's the whole difference.